North America's worst disaster of all time is about to happen. Since the dawn of civilization, violent natural disasters have been a normal part of life on Earth. From modern records alone, many of these disasters, ranging from earthquakes and volcanic eruptions to hurricanes and tsunamis, claim almost 60,000 lives annually. And scientists have just told us to expect these numbers to increase. According to a 2020 study, the Minoan civilization was completely wiped out by a natural disaster around 1600 BC on the ancient Mediterranean island of Thera, which is modern-day Santorini. Will the imminent natural disaster coming to North America be equally as bad? And how soon can we expect this next disaster to occur? Stay tuned to find out. Movies have often been predictors of doom, and when an earthquake gets its own movie, you know it's serious. Many disaster films, such as San Andreas, are notorious for their outrageous carnage and heroics, but in real life, earthquakes on the San Andreas Fault have actually caused significant property damage and human casualties. And according to scientists, the next San Andreas disaster may be tame in comparison to Hollywood's imagination. The last few decades have seen large amounts of population growth, and this has often been linked to large-scale quakes, cracks, and landslides. So, given North America's growth and proximity to this fault, it's been projected that San Andreas could present some serious issues in the not-too-distant future, and it's merely a matter of time. This is supported by the history of large earthquakes that have happened on the Parkfield part of the San Andreas Fault. They've occurred at fairly regular intervals, from 1857 to 1881, 1901, 1922, 1934, and 1966. Estimates show that earthquakes of the highest magnitude occur every 200 years or so. This was calculated based on models that account for the San Andreas Fault's long-term rate of slip and the amount of offset that happened on the fault in that earthquake. It was confirmed when one such earthquake hit San Francisco in 1906, leading to the death of 3,000 people and the destruction of over 80% of the city. This certainly meant it bore looking into. So, a team of renowned geologists compiled seismograph records of the earthquake from around the globe, assessed building damage in San Francisco, examined the local geology, and then synthesized their results into a thorough report, now referred to as the Lawson Report. Several signs point to a chance that history might repeat itself, and such an earthquake might reoccur in the upcoming 30 years, due to the amount of time required to collect slip equivalent to a 20-foot offset. But what is a fault, anyway? And how does this all work? A fault in geology is a fracture or a network of fractures between two sizable rock blocks that move around one another. Faults can be very large. The San Andreas Fault, which spans more than 800 miles, is perhaps the largest in the world. It extends through California for more than 800 miles, beyond San Francisco, and almost as far south as San Diego. In more technical terms, a fault is a piece of the Earth's crust that separates two enormous tectonic plates. Tectonic plates, the broad segments that make up the Earth's surface cracks. By examining fossils and rock layers, scientists can trace the history of plate tectonics. Plate tectonics are the root cause of fault formation, because whilst the crust of our planet is solid, it rests on a moving mantle. This then causes the crust to separate into tectonic plates, which are basically solid chunks of the Earth. They move in relation to one another, occasionally slipping underneath or next to one another. A lot of friction prevents the plates from always smoothly gliding or flowing past one another, which causes a lot of stress to build up during the sliding process. As a result, the plate itself may develop fissures and fractures. Because the edges of the plates are not smooth, friction prevents them from moving past one another. Stress and energy build up at some spots, often along the fault line where the plates rub up against one another. When stress eventually sets in, the fault ruptures and releases the accumulated strain energy, causing seismic waves that humans experience as an earthquake when stress reaches a critical level that surpasses a threshold. The majority of earthquakes occur along the tectonic plate boundaries, which are also caused by these processes. This is also true of the San Andreas Fault, which separates the North Pacific Plate from the North American Plate, two of the largest tectonic plates. Because of the friction between the tectonic plates, earthquakes frequently occur at faults and at their edges. And the San Andreas Fault is unquestionably the mother of all earthquake faults, according to researchers. However, the notion that lateral movement was taking place alongside the plate was still up for debate. In fact, when geologists Mason Hill and Thomas Dibley suggested that San Andreas was actually moving laterally in 1953, almost 50 years later, the hypothesis was seen as extreme. It took another 2 decades for plate tectonics to become widely accepted and for the theory to be proven correct. Of course, there were other significant earthquakes that occurred than those that occurred in 1868 and 1906. This sparked a flood of research on the San Andreas Fault, greatly advancing our knowledge of both the fault and of geology in general. More than 3,000 studies on the problem have been published in the previous 24 years alone. For instance, scientists discovered that the fissure causes earthquakes of magnitude 6.0 around every 22 years. Such occurrences occurred with striking regularity in 1857, 1881, 1901, 1922, 1934, and 1966. But it's hard to know in advance when an earthquake will occur. This was demonstrated here as well, when the earthquake that followed the one in 1966 occurred all the way in 2004. As you know, earthquakes occur when a sufficient amount of stress builds up and is suddenly released. Although it is possible to predict the overall behavior of such a system, it's impossible to predict with absolute certainty when an earthquake will occur. Researchers do, however, have some hints. The San Andreas Fault has achieved a sufficient stress level for a 7+ magnitude earthquake, according to a 2006 study that was published in Nature. The southern portion of the fault, or the region around Los Angeles, is where the risk is most concentrated according to the study. In fact, according to a number of studies, an earthquake in Los Angeles may be long overdue. But how did it all begin? Although the southern portion of the San Andreas Fault has only been there for about 5 million years, the San Andreas Fault began to build about 30 million years ago. The slide rate along the fault ranges from 20 to 35 millimeters per year, which is about the same pace at which your fingernails grow. This speed might not seem like much, and in reality not much will happen if you view it in terms of a few years. On the longer timescales, however, the constant motion of the plates will generate the aforementioned stress and let it out in the form of earthquakes. The problem was discovered more than a century ago. Professor of Geology at UC Berkeley Andrew Lawson discovered the fracture in 1895 and gave it the name Laguna de San Andreas after a nearby lake. Lawson had no idea that it also uncovered a brand new category of earthquake known as an intermediate depth earthquake. Let's not, however, jump the gun. Everyone was aware that earthquakes occur in California. But plate tectonics only became a dominant theory in the 1970s, and it wasn't even apparent how relevant the San Andreas Fault was to the earthquakes. The Hayward earthquake, which occurred in 1868, had recently occurred and left significant damage and fatalities on both sides of the bay. Scientists decided to look even further, centuries back, to get clues based on the heating of the Earth's crust to be able to predict some sort of timeline. The San Andreas Fault Observatory project required the drilling of a sediment core from the middle of San Andreas, which the researchers examined. The researchers discovered a region where the biomarkers indicated warmth approximately 1.9 miles deep in the core. The siltstones and mudstones in that area of the fault were likewise extremely distorted, according to the researchers. It possessed a number of these tiny slip layers, which resulted in a lot of scaly and glossy surfaces, which are characteristics of rocks that experienced numerous earthquakes. It was revealed in the journal Geology that this area of the fault may have been the site of more than 100 earthquakes. Scientists used a technique called potassium-argon dating to examine the rock that had been affected by the earthquakes. This technique makes use of the fact that potassium-40, a naturally occurring radioactive variant of potassium, slowly decays into argon gas. This gas is emitted and restarts the potassium-argon clock when something heats the rock. The amount of argon that had accumulated allowed the scientists to calculate how recently the rocks had been heated. According to their findings, the heating occurred at the earliest 3 million years ago. It was noted that the earthquakes might have occurred much more recently. Experts are still working on refining the potassium-argon earthquake dating technique to reduce that time range. However, the size of the heating suggests that even the central San Andreas can definitely experience significant shaking. Even though the southern aspect is the most worrying, the defect looks to be severely stressed in many segments, which is nevertheless a matter for concern. According to the Los Angeles Times, Thomas Jordan, director of the Southern California Earthquake Center, has previously stated that the fault appears locked, loaded, and ready to go. In a nutshell, there may be an earthquake very soon because the pressures have not been released in years. But just how disastrous will the earthquake be when the inevitable occurs? According to Rick Astor, professor of geophysics and department head at Colorado State University, there are numerous realistic scenarios for major earthquakes up and down the San Andreas fault system, including ones that would be severely disruptive in California. Geologically speaking, the San Andreas fault system is prone to very large earthquakes, but the incidence of small earthquakes over years to millennia is chaotic. As a result, probabilistic earthquake predictions are conceivable, but at the moment it's sadly not possible to predict the size, timing, or even the location of specific earthquakes. Experts say that even if the central San Andreas eventually does not generate enough stress to initiate a big earthquake, there's a big chance it would still serve as a conduit for earthquakes, coming from either the northern or southern portions of the fault. Before you go, let us know in the comments below what your insights are on the imminent natural disaster. And if you've enjoyed this video, don't forget to hit like and share it with your friends. Make sure you subscribe to the channel for more, and click the bell icon so you can get notified whenever a new video drops.
In a stunning celestial event, the Sun unleashed its most powerful eruption in almost 2 decades, sending an explosive solar flare hurtling towards Earth. Known as the biggest solar flare in 17 years, this awe-inspiring phenomenon has taken astronomers and enthusiasts by storm, and so many are asking what happened. Is a solar flare worth being worried about? Does it have any significant impact on our future? We get to find out these answers and more in this eye-opening video. On December 14, 2023, the world held its breath while witnessing a celestial ballet of fire and energy that painted the sky with mesmerizing colors. As captivating as this display was, it seemed as though the universe had chosen to wield a palette of colors to adorn the sky. Yet, beneath the breathtaking hues, a much more significant event was unfolding. This is the story of the largest flare ever experienced by the world. Before we talk about the phenomenal event that unfolded on the 14th, it's pertinent that we talk about solar flares to show how and why this one is the most spectacular yet. Solar flares are what some might refer to as cosmic or celestial fireworks that grace the sun, but it supersedes all of that. Indeed, it truly involves the sun, but it isn't just a surface affair, as there are many cosmic energies in the course of a solar flare. The history and strength of all solar flares are all linked to the sun. The only reason we have come to know about them in depth is because we've come to understand the sun's dynamics even better. It turns out that astronomers had long been peculiarly captivated by the darker and cooler areas on the sun's surface. While the intent behind the interest was solely out of human curiosity, it wasn't until the 19th century that technological advancements started to unravel the relationship and mysteries of solar flares. This brings us to the question, what are solar flares truly? Solar flares are eruptions of intense energy on the sun's surface, caused by the release of magnetic energy accumulated over a long period in the sun's atmosphere. While numerous solar flares have been recorded over the years, it's safe to say that the occurrence dates back to the beginning of creation. In recent years, researchers, such as Fusa Miyake, have been able to trace solar flare activities from ancient times by comparing tree rings. According to their findings, the most powerful solar flare to ever hit our planet occurred approximately 14,300 years ago, bringing a solar storm infused with high levels of gamma rays, which impacted the Earth. Solar flares are classified on a scale ranging from B to X, each letter depicting the flare's strength. The X solar flares are regarded as the most powerful solar flares, while the B solar flares are weaker in magnitude. In most cases, the X solar flare eruptions manifest as bursts of light, giving off X-rays and charged particles around the Earth's atmosphere. What category do you think the recent December 14, 2023 solar flare falls under? You guessed it right, the X series. NASA specifically designates it as X2.8, considering it one of the most recent and strongest solar flares ever experienced. Why does the X2.8 solar flare matter so much? Well, the X2.8 is being talked about because of the unprecedented nature in which it occurred. Over the years, scientists have guaranteed a certain level of understanding about many phenomena occurring in and outside our stratosphere. With the event of the next occurrence of a solar flare being one of them, the X2.8 has once again proven that our understanding is much more limited than we imagine. A big solar flare is expected to arrive in the year 2024. However, it came way sooner than expected, defying all scientific logic behind its occurrence.
The more we put up in space, the more at risk our communication, our space-based technology.
This begs the question, on what basis is there supposed to be a solar flare, and what are the dynamics involved? Predicting phenomena such as solar flares or a few others caused by the sun is only possible due to the solar cycle. Scientists deduced this cycle by observing the series of activities unfolding on the sun over 11 years. And you know what? Two distinct phases mark the solar cycle. This includes the solar maximum and the solar minimum. The sun becomes very active at the solar maximum, which happens to be the cycle's peak. Upon observation, one would find more sunspots and solar flares, and the sun then tends to give off more radiation. It's an entirely different thing for when the cycle is at solar minimum. At this point, the sun becomes very calm. One could even say it hibernates at this period. During this period, there are likely to be very few sunspots, and any existing flares are notably small. One might ask, what role do the sunspots play in this, and what are they? Sunspots are dark patches on the surface of the sun, also known as anomalies. These patches emerge where intense magnetic fields inhibit the upwelling of heat from the sun's interior. Think of it as a breakout on the face of the sun, waiting to pop. When it finally pops, it produces what we know as solar flares. Interestingly, the occurrences are way more connected than they appear to be in the eyes. For a solar flare, there must have been enough sunspots to stir up a flare, where the flare would originate from. For sunspots to exist on the sun, the solar cycle must be at the maximum. Do you get where this is going? That's the summary of what is meant to happen before X2.8, or so we thought. Surprisingly, that's not what happened. Instead, the X2.8, which happens to be the biggest solar flare in 17 years, occurred when the solar cycle was at its minimum, and that's what the commotion is about. According to NASA, the sun emitted the solar flare precisely at 12:02 p.m. The ability to capture an image of the event was made possible by the Solar Dynamics Observatory, which was pre-installed to study the dynamics of the sun. It's safe to say that if the satellite were not in space and scientists relied solely on telescopes, they would have missed it. This statement stands because they never saw the flare coming. What are the implications of the X2.8, and how does it affect the Earth? As an enthusiast or astronomical scientist, you must know that a solar flare as big as the X2.8 would go out with a bang. And so, what we are going to narrate is simply what happened when the solar flare went off on Thursday. In the video, if you recall, we narrated how the forces of the magnetic field tend to inhibit the upwelling heat. What do you think happens when this heat can no longer be suppressed? Aside from the solar flare, which happens, there is a repulsion of the magnetic field, which is responsible for the sunspot. Owing to the magnitude of the solar flare, there must have been quite a powerful magnetic field suppressing the heat in the dark spot. However, what happened to all of that energy? Where did it go? As they say, energy can neither be created nor destroyed. Instead, it's converted from one form to another. For us on Earth, let's just say the conversion and release of magnetic force weren't as favorable. Since most of our machinery runs on electromagnetic pulses, they were seriously affected. This includes radios, communication equipment, electrical grids, and spacecraft. For one, the SPWC explained how the X2.8 solar flare was strong enough to cause some high-frequency radio to black out. Within the release time frame of the solar flare, communication from both ends of the radio was not possible. Still, saying that's all would be an understatement. There was also a major interference with the aircraft's radio communication system. They were not only unable to communicate with the air traffic control tower, but they were also unable to establish communication with other aircraft. If not Lady Luck had been on our side that day, it's possible that we would have recorded a few plane crashes. There's also the issue of the railway signals. According to a specific study, it is possible for a solar flare, combined with a geomagnetic storm, to impact rail signaling and potentially cause malfunctions. This implies that instead of observing red signals, one might see green, and vice versa. Such a scenario could lead to absolute chaos in cities with a strong reliance on railways. and there is a high likelihood of significant damages being incurred. Somehow, the X2.8 event is related to the Carrington event that occurred in 1859. The Carrington event signifies the occurrence of the most significant geomagnetic solar storm in history. In fact, the impact of the Carrington event surpassed that of the X2.8 in both destruction and magnitude. It was named after Richard Carrington as a tribute to his observational skills. A day before the event, Richard had been diligently observing the sun and reported witnessing a powerful coronal mass ejection near the surface. However, due to the limited understanding of the sun during that era, the gravity of what was about to unfold went unnoticed. So, let's break it down a little. Firstly, you should know that coronal mass ejections are massive bursts of solar wind and magnetic fields which arise above the solar corona. It's true that these phenomena often follow solar flares, but not necessarily. However, it's what generates the charged particles that make their way to Earth, causing geostorms. For the Carrington event, the coronal mass ejection unleashed shock waves that traveled through our solar system, resulting in a significant storm in Earth's magnetic field the following day. This storm led to the frying of telegraph circuits and the electrocution of operators. For some, it was the first time witnessing auroras, as polar light shows reached unprecedented locations. In terms of damage, it's safe to assert that the Carrington event deserves recognition. Fortunately, during that time, we were not heavily reliant on electromagnetic machinery like telegraphs. If a similar event were to occur in our era, the world might face a temporary blackout, potentially causing widespread chaos. Considering the various adverse effects that the X2.8 and Carrington event had on our planet, one can now comprehend the gravity and nature of the event. These effects are something that can be prevented with several measures in place. However, the unpredictable nature of the X2.8 is what makes things much scary. Suppose the biggest flare of the decade could have this much impact on Earth. What's to say that we can foresee and predict the occurrence of the next solar flare and the one after that? And if the release is even way bigger, would we be able to brace ourselves for impact or just be sitting ducks? These questions remain unanswered. This goes a long way to tell yet our limited understanding and knowledge of our solar system. Looking at things from a brighter and more colorful side, it's worth noting that solar flares are also quite beneficial. When looking at the astrophysical benefits, solar flares release many charged particles. These particles are beneficial in propelling spacecraft and saving the fuel needed to make it to space. Then, there are the auroras or northern lights, generated by the interaction between the solar flare and the Earth's magnetic field to illuminate the polar skies. Describing the view as nothing short of breathtaking would be an understatement. It is simply one of those celestial, magical scenes that anyone would love to witness. In conclusion, the sun reminds us to learn about its dynamics and actions, and we can only do that by paying attention. Stay tuned for more content like this by liking, commenting, and subscribing. Until next time, have a wonderful day.